B is what? Div A cross B. No. Div of A dot B, sorry. Grad of A dot B is one of the identities. How do we expand this? This is expanded as Abi. That is A plus what? You cannot interchange this with this. That is A dot what? Interchange that with B. When interchange A with O, but it has 4 parts plus B call what? B cross call A. It's very easy to remember. Don't change it to this. And again, interchange it with this. That is A cross what? Cross B. We need this because we want to get another form of this equation. I mean, the equation of we want to get another form of Navier-Stokes equation. So we need to make some substitution there. So this is very important. What happens? In the case where A is equal to B, let us not set A is equal to B is equal to Q in this above equation. So in this identity, then what we obtain? So that means this changes to what? You can write this as that's Q dot Q, isn't it? That is Q squared because this is Q dot Q because Q dot Q is Q squared. Once you know that, is equal to, of course, everything here that is now Q, they are the same. That's Q del Q plus Q del Q plus Q cross call Q plus Q cross call Q. Of course, you can see that means you have 2 of this and also 2 of what? 2 of this. So this can then be summarized as, so from this we get an enabling equation from this which is the same as what? So this is the same as saying that what? So these 2 of this, 2 of this, so you can now divide. That means half of what? Half of Q squared is equal to Q dot Q plus what? Plus Q cross Q. So this is well known and it is established from this. And don't forget, even this is one of the identities that I gave to you people in class, and you are yet to submit. And this now reminds me that all these identities you are supposed to prove. We proved some in the class, so you are supposed to prove them and send the solutions to me. So with your matric number, your full name written. So that reminds me, you are yet to submit, even though I have given it to you in the class. So try to remember to solve them and send them to me. So there's no problem. So this expression is well established. So we are now going to reconsider our Navier-Stokes equation. Let us and now make some substitution because I intend. This is what I want to do. I want to substitute for this. I want to substitute for this expression in the Navier-Stokes equation. See it. This is the expression I want to substitute for. See it here. It's still here now. Oh, please, this expression is wrong. Try to correct it. This is Q. Even you will have noted that this expression is what is here. You can see if we remove Q, remove this Q, it is then you recover this. So that is error of writing. So you can see this is here. This is actually, if we pull out this Q, the outer Q. It is then you get it. This becomes an operator. So I intend to substitute for this, which is A. I want to replace this in the equation of motion, sometimes for equation of motion, that is Navier-Stokes equation. So let us go back to what is the full expansion again. Full expansion of Navier-Stokes equation, which we denoted by 2 in the absence of body force, is what? So remember, it is what? I have dq dt is equal to minus 1 over rho graph p, is it? Then plus u of what? Of, isn't it? That is nobody force, isn't it? Yes. And also it is what? Incompressible. The fluid is incompressible. Nobody force. I don't want F. Okay? And incompressible means what? So that means it's still here. That means that this is the portion I need. But I will use this now to expand. If we expand this, this expands in an obvious way as what? As that you see there, substitute that q that t plus q dot q. That's the only thing I substitute for, which is this. So this now gives me minus 1 over rho grad p plus mu del square q. Hope this is clear. Now I intend to substitute for this. That is my intention. I will use this expression. I want to use this expression to substitute for that. So in that wise, that means if you make this one the subject, in that wise, that means from here, because this is my intention, so that means q dot del q, are you with me? So that means this is the same thing as well. So I will transfer this to this side. That means I have half of del q squared minus what? Minus q cross cos q. So that is what we want to use here to replace this. Doing so, what we have, if you substitute that, then we can write our Navier-Stokes equations or momentum equation in the absence of body force, and fluid is incompressible. So that means we can write this as what? By the time, just transfer this. To transfer this, that means I'll take the whole of this and plug it here. So by so doing, so if you transfer that, I can write this as q t plus what? So that means plus half of q squared minus what? Minus q cross q. Okay? So comfortably we've done that. So that will be equal to what? Minus 1 over rho grad p plus mu del square q. So you can see clearly from here. Now, don't forget, we have done this before. This is called what? Remember, this is, we call it what? That is vorticity vector. We call vorticity vector. That is vorticity vector. Because vorticity vector, as defined, we worked several examples on it, is what? Is called Q. That is vorticity vector. So in that wise, we can still further rearrange that our last equation can still further be rearranged, and it can now be written as well. So I want to put this here. I want to double jump. Since I know this, I want to transfer this. I want to transfer this to join this. Because there is grad there, there is grad there. So I can write this as di q that T minus what? Minus Q cross zeta. Because you know this represent what vector is now equal to what? Is now equal to minus 1 over rho grad P. This equally as cross to this side, then minus what? Also minus 1 upon 2 grad Q square. You can see grad. This is grad, this is grad. So if you like, you can link them together. Then plus nu del square Q. This is another form, but this can as well still be written neatly. This is also another form of Navier-Stokes equation. This is another form of Navier-Stokes equation. So if you like, so this is another form. Just let's do it. So this is another form. This is another form of Navier-Stokes equation. This is another form of Navier-Stokes equation. So if I like, I can call this one 2 prime prime. That's another form of Navier-Stokes equation. Also, we have done it before. Recall that grad P I don't know. Recall. Also recall that 1 over rho grad P is the same thing as what? The same thing as dP over rho. I think this I've told you in the class, and I think we even proved it. We proved it in the class. It's very easy to prove. It is very easy to prove. You can continue. You know, this is in vector form. It's very easy to prove because you know this has 3 components. So you can write this 1 over rho. That is di x, di y, di z. Because this is the direction for this. Then P is equal to again. This is also what? There are 3 components: di x, di y, di z of what? Of P over rho. Of course, if you consider this side, for example, and consider this, because there are 3 components, so you can see clearly that this one will be what? So this is 1 upon rho di x of what? Of P. Are you with me? So I want to consider this and this. So that is the ith component. Component along I. So you can say this is J component, this is I component, J component, K component. Okay, this I component, of course you know that, J component, and also what? And also K component. So I consider only this. So this now will be what? It will be equal to what? Di x of what? Of integral dP the what? All over rho. Of course, from fundamental law of integral calculus. You can see this is integration. This integration is derivative. So you can see, you look at fundamental law of integral calculus. This all is valid. From fundamental law of integral calculus, you can see that this is derivative and this changes to what? This it holds. From fundamental law of integral calculus, you can see that. You see, this is integration and also derivative. You can see this integration will remove derivative for fundamental law. Here they see it. This is simply what? This is 1, 2, 3 equivalent to what? So this, see, this is integration. When you integrate and you differentiate, it's like you have done nothing. So this simply changes to what? This simply changes to what? So dp, this 1 over rho of what? Of di p di x. It follows because this, so consider, so but you can still prove it. So since if it is true for the I component, the same trend for this and this, and finally this one. So this is generally valid. Now in view of this, we can now write, in view of this, we can write our equation 2 prime prime can be written as what? Equation 2 prime prime. 2 prime prime is another form of NS equation. NS equation can now be written as what? So we can now write it as di q di t minus q cross zeta. So I cannot link this together. I can link this together because I know that this can be written as this. So that means that is equal to what? That is equal to minus grad of what? Of p dp over rho, then plus what? Plus q squared upon 2, okay, plus what? Plus new what? So that's it. It is obvious because you can see that because I've replaced this one. This has been replaced with this now. So that is why it is now this. Because this one is under the natural one, so you can throw this one that is. So that is that. And please take note that this is a scalar, whereas this one is a vector. Take note of that. This vector, scalar, scalar. So everything here is grad of the scalar. So this is also very important. There's an important. But the problem is, if you want to add body force to it, you can always add body force to it. So this is also another important block of Navier-Stokes equation. So I can say this is 1, 2, 3. It's also what we have derived today. So all these are very important. Now finally,